This is talking about ascent and descent physiology. What happens to air spaces as we descend or ascend. Most of what we have to acclimate to in diving is pressure, expressed as pounds per square inch, PSI. Right now at sea level, we have pressure exerted on all objects here at sea level, caused by about 10 miles of air stacked on top of each other. All these molecules weigh something. At the bottom, we've already figured out that it weighs 14.7 pounds per square inch. That's the weight on any objects here at sea level. Since this is caused by our Earth's atmosphere, we refer to this also as 1 atmosphere of pressure. Sometimes you see it as 1 bar. They all mean the same thing. 1 atmosphere is 14.7, 14.7 is 1 atmosphere. So what this means is that here is sea level. And the higher up you go, the less pressure there is. The most is right here at sea level. Up here, 5 miles up, it may only be 10 pounds per square inch. But every object here at sea level is going to have 14.7 pounds of pressure on it. So if we measure out square inches, for example, on this table, each square inch has 14.7 pounds of weight on it. And all the square inches on this table is what? Probably 300 or so square inches. And each one of those, 14.7. So the total pressure on this table right now is probably about 5 tons. Top of my head is about 500 pounds. We don't notice it because it is equally applied pressure. There's as much air pressure underneath that table pushing back up as there is pushing down. Same thing with my body. There's as much pressure on the bottom pushing back up, so the pressure cancels out itself out. All the forces cancel out. Solids and liquids, the molecules are essentially all touching. Of course, in the solids, the molecules are locked together, so we can't get our hand through it. But liquids, the molecules slide on each other, so we can move our hand through the liquid. So if we start increasing the pressure around these objects, either solids or liquids, nothing really happens. For example, let's take a balloon and fill it up with a liquid, water. Imagine all these molecules are touching. If I applied unequal pressure, just top and bottom, I'm going to crush that balloon. I'm going to squash it. But if I apply equal pressure all the way around it, if I start increasing the pressure, nothing happens. This force is pushing against the skin of the balloon. That's transferring the force to this molecule. That's transferred it to this molecule. Same thing's happening from the opposite side. When they meet in the center, they cancel themselves out. So if we increase the pressure on a liquid or solid, nothing happens. Or as another analogy, a swinging door. I weigh 180 pounds, someone else weighs 180 pounds. We both lean on each side of the door. We aren't going anywhere. We're canceling each other out. Okay? Now, let's say I take this balloon situation and do it a little bit differently. This time, let's say I fill it up with air. Air has a lot of space between the molecules. I can't feel the air molecules right now. There's a lot of space between them. Unless I'm going real fast in the car, stick my hand out, then I can feel. But if I apply equal pressure to this balloon now, that's filled with a gas, air, equal pressure all the way around, start increasing. what happens is this force pushes the skin of the balloon in. This force over here is pushing the skin of the balloon in. This one and this one. As I increase the pressure, it keeps making the balloon get smaller. I'm pushing the molecules of air towards the center. Now the air is going to get more dense as I get towards the center, but now I'm making that balloon small. I'm compressing that balloon. So any air spaces are going to get compressed if we increase the pressure, get smaller. If we decrease the pressure, they're going to get bigger again. So how does this apply to us in diving? Well, we've got some air spaces associated with us. We got a couple sinuses up here, we got a couple here, we got a couple here. Our middle ear is an air space. Our lungs are air spaces. Our mask, when we got it on, is an air space. All these air spaces, as we increase the pressure around them, they're going to get smaller. In diving is what we call squeeze. Nice descriptive term. Sinus squeeze, ear squeeze, lung squeeze, mask squeeze. If we get sinus squeeze, we get blood and fluids forced into our sinuses. So after a dive, we may have some blood coming out of our nose or we're spitting it up. Our middle ear, I think most of you know what happens there. As the pressure increases, we start feeling extreme pain on our ears, in our ears. Eventually, what's happening is the eardrums are getting pushed in, so eventually they will rupture. Our lungs, if they get compressed too much, they collapse. And even if we reduce the pressure, they won't open again. Collapsed lungs, lung squeeze. The mask, when we got it on, our eyes are pushed into that mask. So we can end up with bloodshot eyes or black and blue eyes. Fortunately, all those air spaces are connected by tubes to our lungs. So if that pressure change is not too rapid, those air spaces are going to equalize automatically. Every day we have, not every day, but every now and then we have a pressure front move in. You've heard of high pressure fronts, low pressure fronts. They're coming slow enough though, as that pressure builds up. It flows into our lungs, the extra molecules, and then from our lungs they flow up through these tubes into all these air spaces, automatically equalizing them. We were actually designed for walking as humans. Not for maybe running, but not for driving, flying, or diving. I don't know if any of you have ever been up on a mountaintop and you walk down, you don't notice a thing. But if you're driving down that mountain, you notice some pressure changes in your head. Definitely you're going to notice them when flying, and definitely you're going to notice them when diving, because water weighs a lot more than air. In fact, it only takes 33 feet of water to weigh the same as 10 miles of air. So if we go down 33 feet underwater, we're picking up another 14.7 for a total of 29.4, or 2 atmospheres total. 1 water, 1 air. 66 feet, 3 atmospheres total. 2 waters, 1 air. 99 feet, 4 atmospheres total. 3 water, 1 air. So, going down just 5 feet underwater is equivalent to coming down from 20,000 feet in a non-pressurized plane in 3 seconds. So, the pressure change is much more rapid in the water than it is on land. So therefore, we have to be more concerned with how to equalize these air spaces, because if we can equalize these air spaces, all this will not happen.